Hey everyone, and welcome to the advanced track. We're here today with the second session of the advanced track. They're two independent sessions. So yesterday's was about optics, and today we're going to learn about understanding memory usage in Haskell and debugging kind of issues with that. The session is again led by Well-Typed, one of our Zurich partners. And from Well-Typed, we have Matthew Pickering and Ben Gamari, who are two renowned wizards of GHC magic. If you have any questions during the talk, you can ask those in the memory usage channel in Discord. So Ben and Matthew, the floor is yours.
Thank you, Jasper, for the kind introduction. So as Jasper said, I'm Matthew, and this is Ben, and we're going to be running the memory usage workshop today. And it's actually quite nice to be presenting this at Zurich because I started working on memory profiling tools at Zurich 2 years ago. If you cast your mind back to the sunny shores of Lake Zurich 2 years ago, that's where eventlog2html started. So it's really nice to be completing the circle and giving everyone an update and a chance to get to use the tools I've been working on memory usage for a few years now. So about me and Ben, we both work for Well-Typed. Well-Typed is a Haskell consultancy, and both me and Ben work on GHC nearly full time at the moment, maintaining it. And so if everyone probably mostly knows what Well-Typed's all about. We can help with any Haskell problems. So if you have any consultancy needs, then info@welltyped.com. Especially if you have memory usage problems, because then I get to work on some interesting memory usage problems potentially. So about this workshop, there are 3 different parts to the workshop. So firstly, we're going to start with a general introduction to how the runtime works and how Haskell values are represented at the runtime, because in understanding how Haskell values are represented at the runtime is quite crucial to understanding how to interpret memory usage profiles if you have a problem with your memory usage, and understanding things such as how OS memory relates to actual heap, how OS memory relates to like the live memory in your program and things like this. Like if you have a basic understanding about how at a low level Haskell values represented, then it can make your life a lot easier. So Ben's going to do that part, and I'll be in the chat to mop up any questions that anyone has and pass them on to Ben if needed. And then after that, it's time to get our hands dirty with eventlog2html and Ghd Debug. So eventlog2html is a tool for visualizing heap profiles in Haskell, which I've been working on for a few years. And this is the best way, in my opinion, to get a high-level view about memory usage in your program. So we're firstly going to explain how eventlog2html works and how you can use that to get a high-level view of what's taking up the memory in your program. And then after I've explained the basic principles and how you might like to interpret these profiles and some of the cool new features we've added recently, then there's some exercises as well where we prepared a sample application which is reasonably complicated, which may have some memory usage problems. It might not, but I'm just saying it might. So we might want to run a profile. We're going to run a profile on that and see if we can use eventlog2html to work out what's happening. Unfortunately, with eventlog2html, we might not get to the root of the problem. So it will then, after we've used eventlog2html to look at the high level, we're going to try and use Ghd Debug to get to the low level nitty gritty of our memory usage issue and see if we can use Ghd Debug, which is an even newer tool which only works with Ghd 9.2, in order to ask some very precise questions about memory usage and get some very precise answers. And that will allow us to perform some very precise fixes to our program without having to guess about what to fix or how to fix it. At least that's the goal. So in the third part of the tutorial, I'll explain how Ghd Debug works and how to run some simple analysis scripts using Ghd Debug, which will allow us to fix the issues in the sample application which we prepared. Do you think that sums things up, Ben?
I think that's good. Yeah. Should we quickly say, obviously, as we sort of proceed through the tutorial section, it'd be good if people could start to build the environment that we'll be working with later for the actual tutorial aspect of the talk. So if you could I left the link in the channel, clone the repository that I mentioned, and simply start to follow the instructions, and don't hesitate to holler if something blows up in your face.
Yes, so if you're using NixOS, then the instructions will probably work, but might take longer than the length of the tutorial. So congratulations if you have already set up the environment. Good job. Other than that, there are notes about everything that we're going to talk about in this document. So it should be possible to somewhat follow along, even if you can't try the examples. But really, like, getting a hands-on view of what's happening will be the most useful thing to get really a feel for how to use these tools, in our opinion. So.
Yeah, the other thing I'd also mention is that if there is time at the end of this session, we'd be happy to sort of take a look at or brainstorm with you on how to use these tools for your own problems. So if you do have a program that you suspect might be an interesting workload to sort of characterize and maybe take a look at, then just ponder that, and we can bring it up at the end and potentially discuss concrete examples beyond the small sort of tutorial examples that we'll be looking at today. So beyond that, though, obviously today we're going to be talking about memory consumption, and a large part of understanding memory consumption of your Haskell program is going to come from your understanding of Haskell's memory representation and the layout and structure of the GHC heap. And so today we're going to start off with a brief discussion of the runtime and the structure of its heap. So first, I guess actually I'll first want to sort of ask a question. I'm going to leave 3 messages in the channel. I think this should work. Yeah, if you could just leave a reaction on these, sort of characterizing your experience, level of experience with profiling and sort of generally understanding heap usage of Haskell programs. Okay, so it seems like excellent. All right, now this is sort of what I was hoping for. So this is an excellent group for this sort of discussion. So first, what we can do here is look at how GHC's heap representation and the garbage collector sort of interact, because this is ghc debug, the second tool that we'll be looking at today. It gives you a rather low-level view onto the heap, and the profiler, it's relatively important to be able to understand the structure of the heap in order to understand what the profiler is telling you. So first, we're going to start by looking at sort of the basic structure of the garbage collector. And so as we know, GHC has a copying garbage collector, which is generational in nature. And so what this means is that GHC is going to partition the heap into several sort of subsets of objects called generations. And objects are these sort of an ordering between these generations is generation 0, which we sometimes call the nursery. This is where objects sort of begin life as they're allocated by your program. Then they'll be, if they live long enough, promoted into generation 1, where they will then live for a bit longer potentially. And if they are still alive, then they might move to later generations. And the idea here is that we can take advantage of the fact that most allocations tend to be very short-lived. And this generational structure, because of an invariant that we're going to maintain between the references between these generations and the objects living within them, is going to allow us to do very efficient young generation collections while only having to traverse the entire heap, which is probably going to be much less frequent in the sort of full generation 1 or later generation collections. And so the idea is that the nursery collections are very frequent but very quick, whereas the older generations are going to be traversing more of the heap and consequently slower, but they'll happen relatively less often. And this is important because this is the nature of GHC's profiler really means that we are only going to be able to, we cannot profile objects in the nursery in general, and your profile is only going to account for objects in sort of later generations. So we'll see this a bit later, but the second bit of sort of background that we'd like to discuss here is how the storage manager splits up its address space. So we have GHC is the garbage collector is built on a subsystem called the storage manager, which is responsible for sort of splitting up memory and allocating it into blocks. We call this this subsystem the block allocator. And it's generally responsible for two things. It gives us the ability to, as I said, sort of allocate memory, and it also gives us the ability to sort of associate a small amount of metadata with memory. And this is, for instance, used by the garbage collector for the purpose of quickly looking up which generation a particular block and the objects therein belongs to. So in order to do this efficiently, first, we have sort of a two-layer hierarchy that the block allocator works with. First, the allocator will allocate a 1 megabyte chunk of memory as on an as-needed basis. When we run out of memory, we'll allocate a new 1 megabyte chunk, which we'll call megablock, and then we split this megablock into 4 kilobyte chunks called blocks. And these blocks serve as the fundamental unit of allocation for the garbage collector. And so the garbage collector, as it needs, will request a block or a group of blocks, a small number of blocks, to serve as the nursery. And then the mutator, the program, will actually go ahead and then allocate its allocations into that block in sort of a bump pointer manner. So starting at the beginning of the block, of the nursery block, and fill in object after object until the block is, we reach the end of the block. And that's and so in this way, we have sort of a very efficient allocation scheme, and we can easily look up which generations particular objects belong to. So this brings us to the question of, well, what is a Haskell object? What do they look like on the heap? Since this is ultimately what we're seeking to do here is characterize the size of objects, it helps to understand their layout and their structure. So Haskell is actually quite nice, and it has a very uniform, or GHC Haskell in particular, has a very uniform on-heap layout. So there's specifically, each heap object begins with a small header. Usually, if you're not, we're going to first discuss the sort of non-profiling case, but in the case of that you're not compiling with profiling, this header consists only of an info table pointer. This is a pointer, a single word-sized field that points to a off-heap data structure called an info table. And this info table describes a variety of information about the object's kind, so sort of, is it a data constructor, or is it a thunk? Is it a function, a stack? We'll see there's a variety of options there. And then something about its memory layout. So for instance, in the case of a data constructor, it will describe how many pointer fields the constructor has and how many non-pointer fields the constructor has. So this header allows the garbage collector to sort of decode the object and allows it to tell which of the fields of the object the collector must trace in order to find its outbound references.
Do you have some diagrams, Ben, of the structure of these objects?
So if you look actually in the, actually, why don't I share my screen? That's probably more useful than
sensational idea, as requested by the chat.
There we are. So if you look at the, here we are. Oh dear, I forgot about the, yeah, okay. Well, that's all right. So the, if you look at your screen now, you'll see that there's, I'm currently looking at the closure structure section of the README of the repository. And you'll see that there's an example here of a simple set of two bindings, X and Y, which show, sort of seek to show the layout of some very simple algebraic data types. So here we have a maybe int, which whose payload is a reference to an int. And so we see right below that what the in-memory layout of this is going to look like. So we're going to see that x, that is this object on the top left, consists of first an info table pointer, which again points to an info table. And this info table contains a bit of knowledge about the structure of the oh no, I'm so sorry. These labels here on the right-hand side are actually inverted. I'll have to fix that after the talk. So this should be the just info table on the top. This should be the I hash info table on the bottom. But either way, we know that yeah, these two are actually just flipped.
And is there any way you could turn off dark mode on GitHub?
Yeah, that is. I had realized I had forgotten to do this. Let me see if I can do that. Yeah. Actually, you know what? Here, let me just try this in Chromium, and I can apologies. I can just log out. There we are. Perfect.
All right, beautiful.
All right. Right. So yes. So here we have on the right-hand side these two info tables, I hash and the just info table, which should be at the top, and the I hash info table at the bottom, which contains, as we mentioned earlier, the fact that these things are data constructors and the number of pointer and non-pointer fields. Following the info table pointer of x, we see that there's a set of fields, and again, the layout of these fields is described by the info table. In this case, just contains, as we know, one pointer field, which simply refers to the int in this case. So which we've labeled y, and likewise, y consists of a pointer to the info table pointer for I hash, which is the int data constructor, and its payload, which is, of course, in this case, going to be an unboxed integer. So it's just a number. It's a non-pointer. Again, I apologize for this confusion here. So this is the layout of two very simple objects, a maybe and an integer. Funcs, and of course, this is far from the whole story. So in general, Haskell programs also contain, due to lazy evaluation, funcs, and due to querying, partial applications. And these are actually very similar to the case of data constructors. In this case, we have a similar sort of program here. We have rather x, which is simply a application of a function, of a binary function. I should have given the type to that. There's actually supposed to be a figure here. I apologize for that. Let me bring that up here. There we are. So here we have f, and f is again an applied function, and f has a single pointer argument. So this is going to be its info table. And then it's going to, the partial application of f, y, is going to then have a pointer to the applied argument, in this case, x, which is going to be, again, an integer. So it's a very similar sort of structure between data constructors and funcs and partial applications. Just in the latter case, instead of having fields, we rather have free variables and applied arguments. Finally, so the last major type of object that we're going to see here, the zeros and ones in the info table. Okay, right. So this is, thank you, Artem. So this is the number of pointer and non-pointer fields of the that the payload. These are essentially a description of the layout of the payload of a closure of type F. Is the function info pointer the only one that puts the info table before the pointer? Oh, I see. Right. So, LFORH, yeah, this is actually something that we're going to, I think you're referring to an optimization that ghc does called tables next to code, where we indeed put the entry code of a function right before, or right after, rather, its info table. So that allows us to eliminate an indirection. This is something that is an optimization. It's not really critical to understand in the heap layout, so I'm going to overlook that. But I might have missed. Fun here is not a. It's kind of an enumeration. It's not actually function code. It was. Sorry. Yeah. I see. I see your point here. Yes. Quite right. This should be there. Apologies. Yeah. Sorry about that. Okay. So, stack closures are there any other questions actually before I proceed? Didn't see anything else. Zoom in the browser a bit. Okay, of course. Right. All right. So the last sort of major class of object that we're going to discuss here is execution stacks. So the stack in Haskell captures sort of the context of execution of a particular thread. So for instance, to use a particular example, if we have a case analysis of some object of some value, case of x with some alternatives, operationally, this case is going to first push a continuation, a frame to the execution stack, which records where the execution is going to return to. That is the sort of alternatives, the code that's going to pattern match on the alternatives and jump to the appropriate one after x is evaluated. And then it's going to, after having pushed that stack frame, it's going to jump to x. So enter the x closure. And once evaluation of x concludes, then we're going to look at the top of the stack, and we're going to then find that at the top of that stack is going to be, again, one of these, the continuation frame that we previously pushed. We're going to return to that frame, and execution will continue. And this is something that happens, well, this is very, very frequent that you have stack operations, and moreover, stacks can grow quite large. Unlike imperative languages, many other languages, Haskell does not have a sort of bound on the stack depth, and so therefore we have a sort of a heap-based stack layout. Thread stacks are chunked. That is, they're broken into fixed size blocks, such that a stack of a thread consists of a chain of blocks. And we're going to then, as we overflow one block, we're going to then, or chunk, I should say, not to confuse us with block allocator blocks, but rather a chain of chunks. And as we overflow a chunk, we're then going to allocate a new chunk, and all of these chunks live on the heap like any other heap object. They have some special layout, but beyond that, there's really nothing special about them. So beyond this, yes.
Perhaps we could tie everything together now and just think like, okay, like, so what does it take to understand the whole heap? Like, what? Right. We know how things are presented at a high level, but like, if we want to start asking questions, like, okay, like how would we, like, where would we start from, and then what kind of things would we have to be able to understand about the heap in order to learn?
So this is what the next. Yeah, we're almost there. So the question here is, in order to understand the space behavior of a program, what do we need to what are the questions that we need to ask, and what are the tools that we need to ask those questions? We generally call this heap profiling. And in general, when we're profiling the heap behavior of the program, we might want to do a few things. There is questions that you can ask about live data of the program. And for that, you need to be able to sort of think about, well, what is the data? What does it mean for data to be live? Well, it means that it's reachable by some part of the program. So that is to say that some part of the program holds on to a reference either directly or transitively, to that object. And in order to actually, so liveness in that sense, in order to build the set of live objects, we can just take and start at a set of roots, much like the garbage collector does, and trace those roots, following all pointers until we've sort of hit a fixed point, until we've sort of traversed all pointers in the program that are reachable from our root set. And what are the roots? Well, typically the roots are going to be things like stacks. That captures sort of the current execution state of the program. The stack does, but it also may be sort of artifacts of the generational model that we described earlier. That is to say that in order for generational collection to be safe, we need to ensure that all references from old generations into young generations are traced by young generation collections. And for this, we have a data structure that records these references called the remembered set. And so in general, we're going to be also need to follow the remembered set in order to, if we're not, that is assuming we're not doing an old generation collection. Oh dear. So let's see. In addition to knowing which objects are live, we need to know something about their types or where they came from. And so in order to understand this, there's a few things that the runtime system provides for us. For one, the info table records the data constructor name of each data constructor in the info table, such that the profiler can then use that information to provide more useful feedback to the user. And in addition, we have some means of sort of annotating the program with user-named, what we call cost centers, as we'll see in just a moment. And so this allows us to provide, to ask the questions about what sorts of objects are present on the heap and where they were allocated, which is, of course, two very important questions, being able to figure out why and how to fix a potential space issue. And these are the questions that tools like ghc debug and, as we'll see, eventlog2html can help us answer. So in order to ask these questions, in order to, we need to sort of make these a bit more concrete. And so what we really want to know here is if we have an understanding of the program and sort of a mental model of what should be alive when, and we find that our program does not match that mental model, that is to say that we see an object that is alive at a time when we expect it not to be, well, there's a few questions that we need to ask. We want to ask, what is retaining the object that we expect not to be live? What is the sort of structure of the objects that are contributing this, the size that we're observing? And where in the program are these objects allocated? And in particular, where are the retainers allocated? This can also be a very useful question to ask. And so these lower level questions are the ones that ghc debug, as we'll see later, allows us to answer. And so these two tools work very nicely together, allow us to ask sort of high level questions about what's on the heap, and then really ghc debug can let us drill down, exploring more specifically what and where and what the shape of the heap graph looks like. And so what we're going to do today is we're going to start with a discussion of eventlog2html. And in order to, eventlog2html at its core is really a front end for ghc's cost center profiling machinery. And so we're going to start by looking a bit at the cost center profiling mechanism provided by the runtime. And so, as you all know, as you may or may not may or may not know. The GHD has a built-in heap profiler, which we call the cost center profiler, or generally the heap profiler. And it's generally capable of taking samples of the heap, snapshots of the heap, at various points throughout your program, and sort of building histograms of the contents of the heap, broken down by several potential characterizations, and these include things like the approximate type of the object. So, for instance, how many integers are on the ints are on the heap, how many strings, or rather, how many lists, how many map nodes, etc. There's closure descriptions. That is to say, things like data constructors. So, just constructors would be are one closure description. Funcs are another. Functions are another. And finally, as I referred to earlier, this mechanism allows the user to sort of name or lexically name lexical scopes of your program, giving them what are known as cost centers. So of these, the cost center breakdown is often the most precise, but it also is a barrier to optimization. And so generally, especially when in programs where things like Fusion or very sophisticated optimizations or simplifier optimizations are in use, it can be necessary to use cost centers very sparingly. So while they're very precise and can be very helpful in understanding where allocations occur in your program, it's often very arduous to use them because you need to sort of do you often can't use the automatic strategies that GHD provides to introduce cost centers, like the fprof auto strategy, which essentially applies a cost center to each binding, or fprof top, which applies to each top level binding. You can't easily use these since they would interfere with optimizations that would then change the runtime behavior of your program and potentially skew the profile. And so the alternative that often historically ended up using is to insert cost centers manually. But this is a rather arduous process in a large system, since you have to sort of start at the top level and drill your way down over successive profiles, introducing and refining cost centers over the course of your of time. And hopefully, eventually, you'll find sort of a small enough cost center that you can wrap your head around the heap behavior of it. But this is a rather long process. And so to address this, in 9.2, there's a new feature which we call info table profiling, which allows us to get sort of the best of both worlds. It gives us very precise source location information due to as we having cost center profiling, but without the sort of runtime overhead and barrier to simplification that the cost center profiling mechanism incurs. So if we consider that to see how this differs from the traditional profiling mechanisms, let's just look at a classic thunk leak like this one here. So we have a function here which is going to sum up over sort of a bunch of integers that that are sort of bucketed by some variable by some label A of type A. We want to return a map of the sums of all of the A's. So what we're going to do is we use of course, the from list with, but it turns out that we use the lazy version for some reason. And this is, of course, going to end up producing a whole lot of plus funcs. We're going to end up with not forcing the additions. So instead of building a very small integer data constructor on every reduction, we're rather going to build up a chain of funcs of successive additions, which will only be forced when we actually force the final result, which is obviously not what we want. If this list were very large, then we'd end up with a very large intermediate heap. And so if we threw such a program or through the traditional heap profiling mechanisms at such a program, we'd find that hy identifies the leak unhelpfully as type star. And this is pretty common, especially the type the sort of notion of type that the profiling machinery uses is somewhat approximate, and things like funcs will often throw it for a loop. So we find that things, you see things like star, which is pretty much, I don't know, to the profiler, reported in your profile. If you rather asked for an HD profile, this is the closure description breakdown, then you'll see something appear in your profile that identifies some GHC generated name, which in principle you can look at the STG dumps to find this name and figure out where in your program it came from. And it does give you helpfully which module it came from, which is quite nice, but this is still not particularly helpful. It's not a source location, so you have to really dive into GHC internals in order to get insight. And again, you can use HC to provide a sort of source location, but if this program is buried somewhere inside of a larger system, then it can be quite difficult to actually find that sum_sox is even the bit that you want to be, or its surrounding code is the bit you want to be looking at. So by contrast, info table profiling gives us three features which allow us to identify this leak pretty readily. First, it gives us a new breakdown mode, HI, which collates the heap allocations by their info table identity. It gives us a new GHC flag, F distinct constructor tables, which gives us, which tells the code generator to, rather than produce a single constructor, info table per data constructor, so as there's one info table for just and another for ihash, it will rather produce a new info table per each constructor allocation site. And so now all of a sudden we have the ability to, by the info table, infer from which allocation site a particular constructor allocation arose from. And finally, we have this third flag, F info table map, which tells the code generator to produce an auxiliary data structure which can be used at runtime to map back from info tables to the source locations from which they arose. And so from these three features, we can compile the program with dash F distinct constructor tables, dash F info table map, and dash HI, and this will give us a nice profile which helpfully identifies the leak as being at roughly the source location. So this is sort of the high-level gist of the questions we're going to be asking and the tools that we have at our disposal to ask them. And now Matt is going to bring us through, I guess, first looking at ghc-debug, looking at sort of the high-level heap structure, and then looking at some analyses we can do on that heap before falling back to eventlog2html and looking at the details of profiling, and then what questions we can ask using ghc-debug.
Awesome. Thank you, Ben. So, right, everyone, it's time to flex our muscles and actually do some programming now rather than just think about programs. And the first thing that I want to talk about is, like Ben has explained at a high level, how values are represented on the heap. But it's still a quite abstract concept. So now we're going to use ghc-debug to actually look at how the values are represented on the heap, so that if you have questions like people were asking in the chat, you can actually just look and see if your intuition matches what actually is happening. So in order to do this, if anyone's set up the environment, now this is the time to get your environment ready. We're going to, I've got a simple program in this screen, in the simple directory, simple app main.hs. And in simple app main.hs, there is a bunch of examples which correspond to some of the similar examples to the things Ben talked about. So for example, there is a func, there is it's the same as the func, but we're going to use a bang pattern to force it to be evaluated, a list, a pair, a function, and some more complicated examples going down. And the idea of what we're going to do is we're going to start running this program, and then we're going to connect to it with ghc-debug, pause the program, and then using the terminal user interface, which comes packaged with ghc-debug, just have a poke around and see if things match up to our expectations. So I'll quickly run through that now, and then we'll have 5 or 10 minutes where you can try doing it for yourself and on your own examples if you wish. And then after that, we'll dive into using eventlog2html on a real live application. Okay, so I've got my program here. What's the first thing you have to do to make it work with Ghd Debug? Well, the first thing you have to do to make it work with Ghd Debug is import the Ghd Debug stub module up here. That's where all the functions live, which allow you to instrument the program. And
Matt, could you make
yes,
the font a bit bigger?
The font a bit bigger. Potentially, someone tells me how to do that.
Yeah.
How do you?
Which terminal are you using?
Sorry.
The terminal font, that is.
Yeah. I mean, I could use VS Code instead. That make? No, I should probably make it bigger. If someone tells me how to make the font bigger, then I'll make it bigger. But I don't have access to that knowledge.
Which terminal emulator are you using?
RxVT Unicode.
Oh.
This might be a crowd. So I mean, I'll answer questions about the heap, but this is getting beyond my knowledge now, outside level of expertise.
VS Code might be a good choice in that case.
Okay,
it might be
I'll jump into VS Code and then try and work out in the break. Right, code.
Yeah, that's what I thought. Yeah, I think URXVT doesn't support
We thought of everything apart from this. At least at least people aren't asking me to try and use light mode. Dear me. Right, where's this folder? Okay, so it's in ghc. Simple. Right. All right, so then, okay.
Yeah, that's pretty good.
Okay, so this is the simple program. We import Ghd Debug Stub. That is the module where all the instrumentation functions live. And then all I'm going to do is wrap my executable with Ghd Debug. Okay, and then that's all I'm going to modify the program. And then at the end, after we've created all these values, I'm just going to insert this getLine clause so that the program will stop executing at this point, so we can pause it and then pass control over to Ghd Debug, which will then take control of the program and request information about the heap, which we're going to visualize. Okay, so in order to run this program, I'm sorry, I have to put up with this small, or maybe I can use a terminal here. Maybe that'll work. View terminal. Yeah. Okay, so in order to run this program, I'm going to just type file run simple, enter a number, and then it pauses for interruption by Ghd Debug. And Ghd Debug creates this socket in this location, which will then be connected to by the debugger. Okay, so in my terminal over here, I'm going to start the terminal user interface with command run 2e, and that will launch this pane here, which lists all the sockets which I've opened in my whole life. Select the first one, select pause, and now I can see the heap of the program. These top items here are the examples which we created in the simple script, and these other ones are other GC routes which Ben talked about. So these TSO objects are to do with stacks and then other various GC routes, but we care about these saved objects. And now we can have a look. So the first one, right. So the first example was a thunk. So the first saved object here is a thunk. And what can we see about this in the user interface? Well, it says it's a thunk. And if we press the right key, we can see that the first argument to the thunk, which is this pointer, points to an integer which is equal to 1,000. And why is that? Well, when I started running the simple script, I typed 1,000. So this is a thunk which has one pointer field which points to 1,000. You can see the difference here in example two. Example 2 is just an evaluated integer, which evaluates to 1001, because that is the length of the list from 0 to 1000. And you can see some more examples, like for example, this is a list. So we can see like, okay, a list is 2 pointer fields, which point to the head and the tail of the list. The head points to integer, which is 0. The tail points to another list, which is 2 pointers, and so on. We can see a pair. We can see how functions are represented. There's a map example. And then there's a slightly tricky example to do with strict data constructors as well. What's interesting about this view as well is that I can see the exact source position that GHD thinks this thunk evaluated from. So it says, okay, this thunk, which has got this name, is this type, comes from this module, came from this source location. And this source location is main.hs 56 22 29. So where is that? Well, that points to here, which is then going to point back to here. So the source location is not, it might not be exactly where you might think, but it gets you really close to where you might want to look. So this is kind of a bit of an aside for people to get started with Ghd Debug. So if people want to try this for 5 minutes and 10 minutes with their own examples, and then we'll jump into using eventlog2html on a real application to answer some more high-level questions about memory usage. How does that sound, Ben?
So if we, yeah, thank you. Yeah, probably try to reproduce the simple example first, as described in the README, and let us know if there are any problems and questions, and then we can proceed.
Yeah, and if there's any more questions, then I can take them. But it'd be useful to this point to just check everything is actually set up properly, and you can actually run Ghd Debug and stuff like that. And then the later examples will be more useful. Okay. Right. So I'll start talking again at 5 to 2. How does that sound, Ben?
Yeah, that sounds good.
10 minutes. Okay.
In the meantime, just let us know how things are going locally. Does anybody is anybody having trouble building the situation, the project first? Okay, that's interesting. I'm reproducing. Which version of Cabal install are you using, Eliforish? Okay.
Okay. Good. So yeah. So when you select the socket, then you press P to pause the application, and then you will encounter the screen that I am currently on.
Okay,
Nothing happens after pressing P. Has anyone had any success?
Yeah.
Well done, Adam. Maybe a light theme, yeah, probably. So well done, Theo. Great job.
You were able to run simple. Okay, interesting. Huh.
What platform are you on, Evan?
Yeah, that's a good question.
FER, are you on? You're on a Mac, aren't you? FER.
if you, okay. Yeah, it should work. Works fine here. Mix shell. Oh. Oh dear. Yeah. What is our current story for Mac support, Matt?
I mean, I've never tried it.
Yeah.
I mean, I don't see why it shouldn't work though.
Christian, could you give some more details on how it's failing for you? It does not exist. Oh, interesting.
Oh, beautiful. And I have a large font. Evan, what happens if you just type cabal build 2e? Does it build anything?
Yeah.
Does that work? It sounds like, yeah. Okay, FER. Maybe, have you rebound the P key to something else on your keyboard or something? I'm not sure. I mean, the number of users of Ghd Debug has just increased by about 1,000%. With such growth, problems are perhaps inevitable.
Yeah. It's not. Oh
yeah. The shell does not work on Macs. I apologize for my lack of foresight in this matter.
We could potentially fix that though. Although on the fly, I'm not so sure, but I can try. In principle, it shouldn't need.
If you're using a Mac, then feel free to control me via requests. I've just spent all my last week fixing issues with the Darwin release, so I should know better.
Hib.os, is it?
Yeah, Evan, it should have done. That was the intention of the script. Did you run cabal update, Andres? You need head.package, almost certainly. Intriguing stuff.
All right. Okay, let me see.
Yes, Sam, yes. So the 2e is more of a toy right now. Like, we're not using it for serious analysis. It's for examples like this where we want to demonstrate what's possible with Ghd Debug without getting into low-level scripts. I'll explain shortly. When I explained the last section, like how you're actually supposed to use Ghd Debug. But the way to instrument your applications, yes, you import Ghd Debug Stub, and then you wrap with Ghd Debug, and that's it.
Huh. Okay, these are the sorts of errors. I expected to have errors. I did not expect to have these sorts of errors. This is, man, very strange. Primitive.
Yeah, so this was always a risk item. Unfortunately, we're sorry. This is cutting edge material, so we had to provide some dependencies which are not not normal. Yeah, I know, Evan.
That. Andres, are you using the Nix shell by any chance, or are you just using your? Oh dear. Yeah, maybe we should have Nixified more of this. Yeah,
the Cabal stuff was not Nixified. I would like my money back, says someone in chat.
Yeah, it would have been. Oh well. In hindsight, it's a compromise, but.
Okay.
Yeah, maybe that's a good idea.
Right. So yeah, I'll go through one more time the precise workings of. Right. Let me. Right. So what was it? RX.
It would actually, yeah, a little bit larger, even still, I would say.
Rather than just this screen then.
Yeah.
Oh geez.
It's the first time I kind of take a hang, quit and attach again. Huh. I can't rule that out, BR Price. It's possible that, yeah. I mean, well, obviously, you see what you see, but yeah, that does sound like a plausible bug. We typically have sort of tested this in a single debugger session. I think we should listen again if.
Yeah, that's how. Yeah, what Ben said is that we should fix this, but no one has yet because I've been the only user.
Yeah.
So. Yeah, but it stops listening after you disconnect. Okay. Perhaps we should. If some people have had some success and reached some kind of enlightenment, then we'll move on for the benefit of people who didn't manage to set up the environment.
Yeah. I can continue to try to help people who are still stuck.
Okay, yeah, let's
Yeah, the Darwin situation is tricky though.
Okay, so at 2, which is in 1.5 minutes, we'll restart with the next section. So yeah, we wanted to try and root out these problems earlier rather than later. It seems like some people have had some success and some people have not.
Yeah, regarding Darwin, I think probably the best way to proceed is to grab the, especially so you're on an M1. Yeah, so in that case, grab the AR64, this binary distribution. Give me one moment.
And if you didn't manage to get it sorted out now, there are instructions in the documents which say like run this and then run this, and you will see this and press this.
Oh dear. I think that the bin dist is now no longer available. Okay, I'll
Okay, let's jump back into some good stuff. And if you're having some issues or still compiling stuff, then you can ask Ben in the chat while I carry on explaining some more things about the old memory usage. And in this section, we are going to jump into eventlog2html. Eventlog2html is the tool you want to use to get the high-level overview of your program. Like Ben mentioned, it works based on the normal heap profiling tools built into GHC. GHC has a sampling heap profiler, which at predetermined intervals after a GC will pause the execution of your program, traverse the heap, and then emit a summary of the heap to the event log. Eventlog2html then takes the produced event log and renders it as an HTML page, an interactive HTML page, which allows you to visualize these samples. So there are two parts using eventlog2html. The first part is generating the event log, which you do by running your program with a specific set of options. And the second part is visualizing the event log and understanding the profile. We are going to care about two different profiling modes today. And these profiling modes are two modes which you do not need to rebuild your application in order to use. The profile by closure type mode is the first high-level way of analyzing the heap, and that reports information about what type of closures are the most prevalent on the heap. So, for example, here is a profile that I generated earlier, and this is a profile using the HT mode, which segments the heap based on the type of the closure. So, for example, one type of closure is a thunk. So I can see that throughout my run program, there was this much data in this much redundancy arising from thunks. So if I had a thunk leak, then what might I see? I might see this profile rising up slowly over time, and that would help me understand how to proceed in debugging memory usage of my application. The second profiling mode we're going to care about is profile by info table, which is what Ben mentioned before. And profiling by info table creates a band for each distinct info table in your program, which gives you a lot more information, but it's very fine-grained. So it can be a bit harder to get that high-level view that you're looking for. So how do I profile the program? Firstly, I start looking at the profile by closure type, -ht, and then dive into the info table mode if possible. Okay. So how do you actually generate the event log, which contains the heap profiling samples? Which options do you have to pass to GHC in order to generate the event log with that information? There are two options that you have to pass to GHC in order to do this. So I am going to, for the purpose of this stream, profile GHC compiling the Cabal library. So I've got this script which I've set up, which invokes GHC with some additional options, and then with some more options over here, which I will now recreate, which dictate to GHC or any Haskell executable that we would like to produce an event log with the heap profiling samples in. Firstly, how the option which we use to generate the event log is -l. -l says to GHC, when I run this executable, please produce me an event log which contains information about what's been happening in the runtime of this application. So as well as containing the heap samples, it's also going to contain things like how many blocks are allocated, how many mega blocks are allocated, when the garbage collector is paused, when threads start, when threads stop, all this kind of low-level information that is useful when debugging the runtime of a Haskell program. But for us, we would like the heap profiling information to be in there. So we also have to enable heap profiling by typing -ht. So the combination of these two options together, well, now when we run the program, in this case GHC, will produce the event log file. Okay, so now I've set up the execution of my program to compile with the two options. I'm going to start running the profile by running the script, and that will set off the compilation of GHC compiling the Cabal library. And we'll just wait a little while for that to finish. GHC is well known as being an extremely speedy compiler with low memory usage, so it shouldn't take an extended period of time. And once that's finished, we're going to get the event log file out, which will convert into the HTML file, and then we can have a look and see what is going on. So I'm just going to. So when you enable profiling at a predetermined interval, it pauses the program and traverses the heap. So if you have quite a large heap and it pauses quite often, then it can cause your program to take longer to run. And that's what's happening in this case. So by default, it will pause your program every 0.1 seconds to perform a heap sample. So if your heap is quite large, then the dominant time will be in profiling the application rather than actually doing any useful work. So in this case, it's not GHC being slow. Don't be silly. This is the heap profiler skewing the runtime. But it looks like we're nearly there. And just be thankful I didn't profile GHC compiling itself. All right. I'm not monitoring Discourse, so I'm not sure if there's a lot of dissent about font size, Ben, or is that issue resolved?
I think nobody's complained yet. I think it's fine from my end as well. Yeah.
Okay, good. Okay, it's done. What is the result? The result is going to be a file called ghc-eventlog. No, it is, and the eventlog file is can get quite large. In this case, it's only 112 megabytes, but if you have a lot of stuff going on, then it can get to gigabytes big quite quickly. But the eventlog file itself is a binary file, so it's not very easy to view like this. So we need some tools in order to visualize it. So if we now invoke eventlog2html and ghc-eventlog, eventlog2html will do its magic, and now we also have a file here called ghc-eventlog.html. And this is a web page which we can now open and see the memory usage. Okay, so this is the memory profile of ghc compile with those two options that we said, and we can see that most of the time there was not actually very much live data in the program. It's less than 150 megabytes, but there was this period of time over here which had this spike, and that might be something that we want to investigate. So now we have the profile. I think the next thing I wrote in my notes was about interpreting the profile. Indeed. So the default view is this area chart mode. And on the x-axis down here is the elapsed time in the program. On the y-axis, it's the current residency at that time in the program. So you can see how the memory profile of your program develops over time. A nice feature of eventlog2html is that you can zoom into specific parts. So we can zoom into this area here, and also you can hover over different bands to see what's going on. So in this period here, there was a large amount of this ghc.types.var.tctypevar constructor, which was alive. Another nice thing about area view is you can click on the legend, and it will isolate different bands. So you can see like, oh, our words actually didn't increase very much over time. And you can also select multiple bands at once. So I can select thunk 10 and our words, or I can select thunk and fun, or I can select, you can depending on like your domain, you want to select different things and things like that. So the area view is like the normal way that people have viewed Haskell heap profiles for generations now, using tools like HP to PS and HP to any and HP to pretty. And this is what most people are probably familiar with. But I was not satisfied. So eventlog2html has some more modes as well. There's some more area views, a normalized view and a stream graph view, which are basically the same as a stacked area chart view, but slightly different rendering. But things start getting more interesting in the line chart view. And line chart view is no longer a stacked view, and what it does is it displays the so for each band, so let's take thunk10, for example. It finds the maximum value that thunk10 ever was during the run of the profile, and then normalizes all the other results based on that maximum value. So a value of 1 indicates that at this point it was the highest it ever was in the whole profile, and these rest of these points, it was only about 80% of the maximum value. Why is this useful? Well, now looking at the line chart view, there's something which is immediately obvious looking at this profile, and that are these bands which increase slowly over time to eventually reach their maximum potential at the end of the profile. And that is something which could definitely indicate a memory leak, which is really hard to see in this stacked profile. You can't see that here, but if I go to the line chart, I can see like, oh, this yellow band is increasing. Oh, that's this one. And then you could go back to the area chart, click on fast tree, and you say, oh, actually, yeah, it was, but it was such a small part of the original profile, I didn't even notice it. The line chart really brings that out to the fore. And I can see like, okay, this is increasing, and what's this one? This red band. This band's increasing. So already we're getting this view is allowing us to see something in the profile that we couldn't see using the stacked area chart view. Something else that I found unsatisfying about existing tools was only the top 15 bands are actually present in this view, and a lot of the allocation actually is in other. But other might be interesting in its own right. Other might contain things which are slowly leaking, which aren't a problem now. But if I was compiling a project which was 10,000 modules big, 100,000 modules big, might become a serious issue. So I wanted to get some handle on what was in other. So the detailed pane allows us to get a handle on every single band and look at each band on its own merit. So in the detailed pane, there is firstly a little spark chart on the left-hand side, which shows you how the memory usage for that specific band developed over time. There's a number which tells you like the ranking of the band. Okay, the 1009 is the highest ranked band. It tells you the label, and it gives you some statistics such as like the integrated size is the total area of the band. So if you have something which is of high residency for a long time, then it will have a higher integrated size. And then some certain statistical measures of that specific band, which may be useful and may not be. I just put them in because I thought it might be useful. But what's the killer thing about detailed view is that you can click to all the smaller bands. And just by looking at these spark charts on the side, you can see things like, oh, look, like datacom.make data is actually slowly increasing over time as well. Or you can see like, oh, look, these two bands are clearly correlated together, like Haskell syntax X for HSAP and WP compose. There's something that relates them two things together because their profiles are very similar. And with the detailed view, you can then start to build up a much better mental picture of how your program relates to each other and how the small things relate to the big things. Because at the end of the day, a thunk leak can manifest in a profile as retaining a lot of random stuff that is not really related to the root cause. But if you go to band 10, page 10, 15 or something, then you can really begin to see, okay, like this very small leak is actually the thing I care about rather than getting the bigger overall picture. So even in this mode and using the detailed pane, we can already get a more low-level view of the memory usage in the program. The final addition to eventlog2html that I've recently made is the heap pane, and the heap pane is different to the other panes because the heap pane now allows us to relate the live amount of data in our program to the OS, like a number which might correlate more closely with the amount ROS reports our program is using, which is something which is traditionally quite confusing to users. So in the the green line here, this is the live bytes of the program. Okay, so the live bytes of the program corresponds almost exactly to the level that the stacked area chart sees. For example, this reports 160. If then we go to here, we'll see that this is approximately 160 as well. So this green line tracks quite closely the peaks and troughs of the stacked area chart. But live bytes is not the end of the story. As Ben mentioned, there was more structure to the RCS than this. Live bytes live in blocks, which live in megablocks. So we also report the block size. The block size is the total size of all the allocated blocks. Once we allocate a block, we control it, and the OS believes that we own it. So that is also memory that the OS attributes to your program. And the block size is higher than the live byte size. And depending on your garbage collection strategy and a few other factors, it will probably be about double what the live blocks is, because in a copy and garbage collector, you need double the amount of blocks when you perform a major collection, because you copy all the live data from one block into another block. So memory, the blocks are going to be about double the live data. And finally, the third number is the amount of mega blocks that we have requested from the operating system. Each mega block is 1 megabyte big, and blocks are then allocated into mega blocks, and the live data is then allocated into blocks. So the number, this number of mega blocks should correspond approximately to the amount of memory that your operating system reports that your program is using. And as we can see, it is about 500 megabytes in this case, which is 3 or 4 times the amount of live data. So this pane allows us to understand at an even higher level about the memory use of our program, and understanding, okay, is there actually some other issue going on that's not actually related to the Haskell values and the live data? It can help you understand, like, is the size of my nursery getting out of control, or things like, do I have a really bad fragmentation problem, and things like that. Understanding how to understand that would maybe take us a bit aside from this talk, but interpreting how these 3 lines relate to each other can also tell you a wealth of information about your program. So I hope I might get. Should I explain this, Ben, or is it too? Wait, Ben, wait.
Oh, okay, there we go.
Okay, right, you're back.
Yeah. I think it's good to keep in mind that, as Matt said, the problem may be that your program is retaining data that it shouldn't, but there's also a small possibility that, and we have seen clients, projects afflicted with this in the past, that the problem is actually that GHC is rather the culprit here, and that either due to some form of heap fragmentation, that the runtime system is responsible for retaining memory, and it's not actually that the memory contains live data. It's rather that GHC simply cannot free the memory that it holds, and that's really what these 3 lines are. That's how to interpret these 3 lines. So if you see the heap size significantly larger than the block size or the live data size, then you know that that's good to keep that in mind. That there may be a fragmentation issue as well. This can happen if you have lots of pinned allocations, for instance. Or
it's something to keep in mind. In this profile, the difference between the blue and the red line is due to the nursery size. But in most Haskell applications, the nursery size is fixed over the whole run of the program. But GHC enables an RTS flag which scales the size of the nursery depending on how much has been allocated, which significantly increases the performance of GHC when compiling programs. And the difference between these 2 lines, which is about 180 megabytes, will be because of the size of the nursery, which I verified after seeing this graph and asking, like, why is there such a big difference? I then went into the runtime and looked at why the difference was, and it was because of the nursery size. So that might be
answer the question, Evan.
So it's a question.
He asked about what was the difference exactly. I think you just answered it, but ask again, Evan, if there's something further.
Yeah, I think there's a slight 10-second delay or something on the stream. So
right,
if I anticipate perfectly 10 seconds before, then it would be a bit of a lag. Okay. So, and it's just now with eventlog2html, be able to see all this information at a very high level, very low level. All I did was plot 3 lines in a graph, and it is so useful for me when looking into memory issues to be able to look at this chart and see, okay, that's what I expect to see, and then delve deeper or lower, deeper or higher, depending on further questions. So, are there any questions about the eventlog2html interface before we dive into a few more things about heap profiling? And then once we've done that, there'll be time for some people to experience more build issues with another example. I'm not looking at chat, Ben, so you'll have to.
Yep, no, I'm on it.
Okay.
Trace event. There.
Okay. Well, let's move on. I'm sure you're battering back the questions in the chat with no issue. Right. So we've now explored the interface of eventlog2html. I'll explain a few more little details about heap profiling and then show info table profiling. I mentioned before that if you don't set the profiling interval to something suitable, then your application can take a long time to run because it will be running the profiling. It'll be dominated by the profiling time. There's a ghc option. The -i option controls the profiling interval, -i. And then you give it a number of seconds. By default, it is 0.1 seconds. But a generally good number is 1 second, I find, if you have a heap which is decently large. And you can also pass the -s flag, and that will report the time taken for garbage collection, which will be dominated by the profiling time when you have enabled the heap profiler. So if I rerun the profile with that, then it probably will complete a lot faster. But we don't need to see all that. This is the sort of output you get with -s, and if profiling is dominating your time, then GC time, as reported by this number, will be significantly higher than mutator time. But that's how to debug your profiling run if it's taking absolutely forever. Okay, another good feature of eventlog2html is the support for markers. So in the event log, there is support for omitting user markers, which has quite a simple API. So if we look at the base library, which
I pasted it as well in the chat. The debug.trace module.
Yeah. So the debug.trace module is well known for having functions like trace show and trace and so on, which is used for debugging. There's also buried at the bottom functions. These functions trace marker and trace marker IO, which will emit a marker into the event log rather than output it to the standard error. So when you call this function, it will place something into the event log which says at this point in the program, this trace was emitted, and then those trace markers will also be shown on the profile. So GHC has a flag you can enable, which will output trace markers. So it's already instrumented. You'd have to instrument your program in its own way, but GHC is already instrumented. And then do you just have to pass dump timings, or do you also have to pass v3?
I think dump timings is sufficient.
Okay, so if I pass dump timings as well, then if I run the profile again, right? So that looks pretty good. In the event log we get at the end, we're going to have lots and lots and lots and lots of markers. In fact, too many markers. So if you have too many markers, then you can also invoke eventlog2html with some options to filter the markers, which we will definitely do, because otherwise there'll be too many. So I can use the -i option, which will filter the marker for a specific substring. Let's wait for that. that run of ghc to finish with all the markers. So I will. I'm not sure which markers to. Maybe I'll try. So now I finish this profile, which says okay. So eventlog2html of ghc.eventlog-i, and I'm going to try parse, but I can't remember what the exact event is called. It might display no markers, which we'll have to reconsider then. But let's have a look. Do the old refresh, and there we go. So now we have some. Right. Okay. Right. So it's parser. So now we have these black lines on the screen, which correspond to the trace markers that ghc put it. So there's still a few too many. I'll give you that, but it's not so bad. So now we can see, okay, what's this big spike doing? Well, if I zoom in here and then hover over the marker, it says, all right, ghc started the parser here for the distribution.spdx.license ID fields. So by knowing how ghc works for the compiler, I can work out that this big lump of memory usage, this big spike, comes from compiling that module. So adding markers can give you a lot more contextual information about what your program was actually doing at the time there was a spike. So it's very useful. So ghc has built-in support for these, but you have to instrument your application if you want to take advantage of this feature as well. Right. So I've chatted about the whole interface now. Let's get into profiling by info table, which is which allows you to get quite a much lower level view than the profile by closure type view. So to use profile by info table, I am going to modify the options that I pass to ghc again, and instead of passing -ht, I now pass -hi. The -hi is the profile by info table mode. In order to use -hi, you should make sure your application is built with -f info table map and -f distinct constructor tables, as otherwise the output will contain a lot of addresses which you will probably struggle to understand very easily. But my version of ghc, which I built here, is built with that information. It is not by default, but the application, which we will profile later, already has the correct flags passed, so it can build the application and all its dependencies with those two flags. And what the info table map flag does is it creates this mapping from the info table to additional information about the info table. So what is the Haskell type? What is the closure type of the info table? What source position is it from? What module is it from? Information like this, information which we might find useful when debugging memory usage. And so this map is created, and it works in conjunction with the event log, because when the event log starts, all the mapping information is dumped into the event log as well. So now we have the information about the info tables and all the sample information in the event log. An eventlog2html can understand all that and create a really detailed profile. This does have the effect of making the event log a little bit bigger for this case. For some applications, it could be a lot bigger, but it's not so much bigger in this case. So eventlog2html, ghc.eventlog-i parser. Let's try that. We cross our fingers as always, and we're good to go. Go back to the profile, give it a refresh, and right, so we have a similar looking profile to before, but now if we zoom in over here on the right, the bands are now these addresses. Okay, so I mean, okay, great. Like, this is even less useful than before, right? Well, you may think so, but let's go to the detail pane, and now we get this wealth of information about each band. And this information is created from the info table map. So as well as the information before about the statistics and the name, there are these three new fields, which now gives information about each band in the profile. So I'll zoom back in so we can see that. So the first thing we see is that the top bands is now only 25 megabytes big. That's the first thing to know about info table profiling modes. Because it's so much more fine-grained, the top 15 bands could be quite inconsequential to the total memory usage of your program. So that's why the detailed pane is even more useful. We see the top band is called stgr words info, which we know is from the constructor type R words because of the constructor type field. And this is a special closure type, special info table, because it's built into the RTS. And how do we know that? It's because the module it comes from is given to this ghc_1.cmm module. And that's why we don't get any good location information from it or what type it is, because the allocation site arises from within the RTS rather than from any actual Haskell application. So this is not actually so useful. So you're already probably looking at my screen and seeing these tasty source locations, and that is a lot more useful. So the second band comes from the label 0x7f3bd05eb618, better known as :ghc.utils misc_43 colinfo. This label tells us that this allocation is a constructor, so far so good, which has two pointer fields, whose name is : Which constructor is that? That is the listcons. So we know that this spike in memory is caused by a lot of listcons from this specific site being present in memory. So which module does that come from? ghc.utils.misc. And where does it come from? Well, I've got the source location now, and it says they come from line 1067, position 5 to 6. Should we have a look at that? Let's have a look. So I go into my tree and look at the module ghc compiler. Where was it? Ben? ghc-utils misc. And I look at line 1057, and was it that line? 1067. I look at line 1067, and then I find at line 1067 there is a listcons. So now I know that this precise point in my program is responsible for that amount of allocation. So I know the strict map function is responsible. Well, that's perhaps not so useful. Strict map is still a general function, but it's still far more information than we could ever work out before about where the memory usage was actually coming from. And knowing a strict map and knowing the domain of my program can get me closer to understanding the actual memory usage of the program. So most of the allocation sites actually have these source locations. I could look at any of these and begin to work out, like, okay, why is it reporting this much? Like, what is the memory flow in my program? Why is this function is clearly called a lot of times if it's doing that much allocation? Why is it called that many times? Well, I might use different profiling tools to work that out, but at least I have the handle to pull on and begin to work out the different causes of my memory issues. So this view.
Sorry.
Yes, Ben.
Yeah, and in principle, I think you could probably, if you didn't know which strict map occurrence was responsible for the the worst of the allocations, you could in principle also add, I believe this should work, an inline pragma to strict map, ensuring that it gets inlined into its allocation, into its current sites, and then at that point the source locations should be distinct. I believe that's true. Yeah. We might need to adjust the heuristics a little bit to make sure that that's always.
Yeah.
But
so the location is not always so precise as was in this example. Like depending on because due to inlining, the actual place to attribute the cost to is the most useful place is not so clear, because you don't want to attribute all the cost into some internal module which gets inlined everywhere. That's not so useful. You want to know where it's inlined into. so the source location heuristic attempts to first chooses the closest span to the actual point of allocation, which arises from the same module as where the allocation actually takes place. That's the basics of the heuristic. So that should account for these kind of inlining situations. And it might not always provide you the most precise location, but it at least gets you close. The information does not lie. It is somehow relevant, and understanding how it's relevant takes a bit of experience to get used to, but it gets you a lot closer than previous tools made it possible. So in the detail pane, the first page is not actually usually that interesting, because it has things like strict map and things which are overrepresented because they're library functions. But in the strict pane, in the detailed pane, clicking through the pages becomes more and more interesting as you get to smaller and smaller bands, because you can see the spark line, you can see the location where that comes from. So just clicking through the pane, through each of the pages, and just looking by can be extremely informative.
And in addition, there are other, if you sort, for instance, by the slope, then
we'll sort by the slope. Let's try that. Yeah. So the slope is the slope of the line,
which is admittedly, it's not always going to be useful, especially if you have a program that has sort of many stages. But in this case, we ideally we'd have a better measure of sort of trend, but this is the best that we have in
I mean, it's not so useful, and I mean,
oh well.
It was a great idea. Like, so here the slope is like gently increasing.
Yeah, and these are all small things, so these are not small leaks, if anything, but still, you can sort of easily spot them.
So obviously in this view as well, you can search. Like, I can search the thunk, and I can see, like, okay, I'm also searching slope as well. Let me refresh. Right, so if I go to thunk, then I can see all allocations, and then have a look at all of these and see, like, oh, actually, did we actually mean that to be a thunk or not? And like having thunks is not bad. Like, if you're having thunks you did not expect is bad. And we've looked through this profile now using these tools, and we have ascertained that most of the thunks in this profile are actually not bad. In fact, they're good, because forcing them causes more computation to happen, or pointless computation to happen, which leads to high residency eventually. So we did not build eventlog2html and ghc-debug for you to search by thunk and then force everything. No, we built it so we can think about the problems, and then you can make precise action about what is necessary rather than a guessing. So if you have to guess, then please open the bug report, because we're past that stage now. We can work things out. You can search for type as well, like search for module, and it's chose things called module. You can imagine now you might use these searches in your own applications. At the end of the day, I know how to do it on GHC because I work on GHC every day of my life. But for your application, things are different, and the searches, the queries you want to perform are up to you. And if you want some help thinking about that, then we can help. But it requires you to think about your domain quite clearly. Okay. I think I've covered most things, Ben, about eventlog2html. Is there anything else that you think is necessary to go into?
Don't believe so. There's one question though. What do the numbers after thunk and constr mean? Oh, I see. Yeah, you want to describe that?
So ctie is closure type. Okay, and there are these. This is a closure type called constr 2_0, and the 2 indicates that there are 2 pointer fields and 0 data fields in the closure type. Essentially, it's a special closure type for when we have 2 pointer fields and 0 data fields. So there are these special ones for, is it up to, I mean, we can see. Constr, okay. So there's 2, 0. I'm also searching module at the same time. Okay. So there's this general constr type as well, which does not have these, which is not pre-baked in. So this type will have more than 2 pointer fields and more than 2 data fields, for example. I don't think I explained very clearly there, Ben. Perhaps you can.
No, I think that's fine.
Okay.
So these sort of conster underscore 2 underscore 0, etc. These are sort of an optimization that we have a special sort of closure type that this is a very common case to have sort of 2 pointers, 0 non-pointers. So the garbage collector has some special logic for handling this case, and that's why they're these special closure types. But they're just constructors, and you might find it helpful to know that there are 2 pointer fields. But if not, then just read it as conster.
Yeah. Right. So now I've given the lowdown of eventlog2html. We've got another application that we're going to try and profile, and this one is more real world. Like, this is quite a lot. It's not a large application, but it has a lot of dependencies, and it's the sort of thing you might actually be working on. It's a simple server application, a simple REST server. So we set things up so that we're going to start the server, connect to a database, and then there's a script which runs 1,000 requests. Right, and what we want to do is profile this and see if we can learn anything about the memory usage of the application using eventlog2html. So the server is in this subdirectory, Haskell Scotty real world example. So I'll get into that now. So we didn't write this application, and it's something someone else wrote, which conforms to this real world API specification, which a lot of different languages have implemented servers for. What it does is actually not that important. And in here, there are a few scripts. So the first script we have is this start Postgres a script which will launch Postgres inside a Docker container, which we thought was the most convenient. And then once that's started, you can start the server by typing run_server. And then once the server is running, it will tell you that it is listening on a certain port. And then, oh dear. No. Okay. And then once that is going, there is another script in here called run, and run will perform the requests. It will perform 1,000 requests. And what the goal is to want to profile the server. Okay, so we'll have 15 minutes now where, Ben.
Yeah, I was actually going to ask, I currently left a comment on the channel. So if you do have eventlog2html 9.2 and ghc 9.2 working, do leave a reaction there. And yeah, I guess, I mean, I don't know, Matt, depending upon how many people do or do not have sort of the ability to reproduce, follow along.
Yeah.
We might want to just work through it in real time. I don't know.
Do you have it working, Ben? Because if you've not tried it yet, then you can.
Let's try. We can do that. Yeah.
Yeah. So the run scripts, which are no, not this one. Here. So the run scripts will then perform some requests, like so, and then what these requests do is not so important. It actually makes some articles and database and so on. But the goal is to profile the server while it's processing these requests and see what we can learn from that. So I'll show up now and I'll shimmy into the chat. Ben will share his screen and he will go through his own process of attempting to set up the profile. But if you have your own setup working, then mute him and do it yourself. And I will be able to provide any help if necessary. Okay, so I have about 15 minutes to do this. And then after that, we'll be getting into using ghc debug to potentially debug some memory usage applications in a web server, depending on what we find. Okay. Great. So I'll shimmy off now. Ben, can you share your screen?
Yeah, yeah. We'll in just a moment. I'm going to try to catch, just finish up the last few. Let me see here. All right. Yeah, that should work. Okay, there we go. Yeah, so if you are trying to build Cabal install the branch, then you have to use a older GHC release. 9.2 will not work. Doesn't currently support. Yeah, that's okay. All right, there we go. Oop. How do I detach you? Oh no. Am I okay? Good. Yeah. I forgot about that. I have an idea. Good.
I'm just gonna get a drink, Ben. I'll be back. Hey, what are you trying to install? Are you trying to?
At the moment, I realize that I do not have Docker on my laptop. I might try to fix that briefly, but I'm exploring an alternative route. If yeah,
You must. I thought you were like the main maintainer of ghc CI infrastructure, which is built on
yeah,
the program known as Docker.
Yeah, I try not to use
So
Docker.
perhaps that's why you don't have it installed.
Yeah.
Jesus. Right. Go back.
Yeah. Let's see here. Docker. Yeah, I could alternatively virtualization. All right, let's hope for the best here. I'm gonna try this. Not sure. If I vanish from the call, you'll know that my NixOS upgrade went terribly, terribly wrong. That's usually not the sort of thing I try to do in the middle of a tutorial, but line 6.
Ben, did you mean to share your screen?
I did, in fact.
Yeah. Okay. I've now.
Yeah. No, that's.
I've shared it. You might increase your font size if.
Quite right. Right,
Perhaps by the end of the 15 minutes, you'll also have got the environment set up.
No. I just did an on-the-fly NixOS upgrade configuration change, and so far things have not blown up. So I think I can. I think we can proceed on my laptop.
Okay, great stuff.
Yeah. Excellent. Oh, that's more services than I would have liked to see there.
Welcome to the future. Right, I'll dive into chat now and see if we've got any.
Yeah, that's good. probably good enough. All right, so let's try this here. So what we'll do, let's first start to run the server here. See how that goes. Oh no, we first need to start Postgres. Okay, very good. Okay. Oh, this is going to be a challenge, isn't it? Okay. Well, here we have the means of sorting this. There we go. There we are. Brilliant. Okay. All right. So we have Docker. Now we can go ahead and run this on the server. All right. And now, of course, yeah. All right. So on this side, I'm going to, well, let's see, run the server. And on this side, we can run, well, let's see, yeah, well, that will be, look at the profile.
I should have got Andres to come and do this, Ben. He's prepared. He set up his Nick shell already.
Unlike some of us, I was trying to keep myself,
All right, you're in.
Untouched, but there
He's
we
in,
go.
guys. He's in.
All right, we're good. So, all right, now we can run. So we have the server running with Postgres, the dependencies are running. And so now I can run our workload.
Right, stop that, Ben. You need to uncomment line 6.
And I forgot to uncomment line 6. Yeah,
yeah. That's my fault.
Yeah, yeah. There we go. We'll try that again. All right. There we go. All right. And now we can, whoop, there we go. Make sure I know what I'm doing here. Let's see here. Oop. Good. This is running with -hi by default. Is that right now?
Nope. It's not running at all with anything. It has the right input table flag set up, yeah, but there's no other profiling flags.
Okay. Yeah. So let's see. Let's actually just look at this in top and see how oh dear, see how bad it is. Okay, can't kill that. There we go. There's htop. All right. So
it seems like you've got bad crypto again, then. You might need to recomment the line.
Okay. Well, it's not that bad of a leak, clearly.
It is not that. No, it's not that bad.
Yeah.
No.
Okay. So
yeah,
there we go.
You've got bad crypto again on your left.
Oh, do I?
Yeah.
Oh, connection refused. Okay.
I'm not sure why that bad crypto is. It might just be because you need to comment line 6 again.
And run server. Oh dear. Oh shit. It's wait, am I on the right? All right, there we go. Yeah, it's already running somewhere. Oh, there it is. Okay, yeah, let's do that again. All right, and run. There we go. Okay, now we have no connection refused still. Oh, this is going swimmingly. Presumably that's because of the there it is. Yeah, okay, no, it was just the IPv6 address. Okay, good. Okay, so now in principle we should be reproducing it. And all right. So let me see. Okay, let's just add -hi to the -l, and we try this again. Is this actually working? It's working. Good. Okay. So now there we go. Now we're collecting a profile. Let it go for a while. I'll kill it. There we go. Run eventlog2html on our, there it is, real world exe, eventlog. All right, and now we can look at the resulting profile, which we ran it for a bit too long. Oh, there we go. Okay, so let's see what we have here. So we have, all right, so we do clearly see that, yeah, it's not terrible, but I guess if we look at the this bottom bar here, we see that, yeah, it's plausible that something's leaking. It's getting, the residency is definitely growing. And if we look here, very interesting. So we see that we have these two lines here are quite, are definitely increasing. How big are they? Integrated size isn't terribly huge, but again, we see that this, you know, even in top, we saw there wasn't a whole lot of growth. And if we as well sort by slope, we see that there we go. Yeah, indeed, there's a whole bunch of things here that are sort of growing monotonically up until the termination of the program. You see that there are a lot of things in request handler, okay, request header rather, yeah. Interesting. Let's see, there's some conduit stuff. All right, so there's a lot of things. I guess it's yeah, interesting. So it's a bit unclear, isn't it? Where there's clearly a lot of things being retained, but they could all be retained from some root that's keeping all of these things alive. You know, it's not clear which of these things is sort of the one thing that's being inappropriately captured. Now, I suppose what we could do, though, we might assume here that the issue is not in WAI. If we assume that that's sort of a trusted, you know, part of our trusted code base, then we could start by looking at where in our own code is growing. That, yeah, there's quite a few things here without much of a, oh no.
Bennett, have you got many info table mapping for things in the actual project? You do. Yeah, you do.
Yeah, you do.
You can see in the profile. Yeah, you can see in the profile.
Yeah. Indeed, but there's not. Intriguingly, there's not a whole lot in the actual implementation of the to-do application.
Yeah, that's what I'm saying. Well,
yeah.
So from this profile, then you can clearly see there's an issue, and you can clearly see that the issue is somehow related to. Yeah, so you can see the issue is related to the stuff in network.y.handler. That's the.
It's clearly part of the bit that's being retained, indeed, but that may be the result of something being retained from our, you know, could either be a bug in WAI or something invoking it, and that something could be the actual application in question, you know, right. the test application. So indeed, so how could we actually narrow that down further?
I mean, it might be interesting to look at the line chart view as well. Initially,
that's a good point. Yeah, there you go. So here we have it. We see that there's a sort of 4 or 6, I suppose, interesting cases here, and I think these are probably let's see. If we look at, let's just try to pick those out. So there's one, 2D E160. I can search by that. There we are. And oh no.
Well, yeah. So that one has no information, and I'll discuss a bit why that had no information shortly.
Yep. Excellent. And now, let me see. Oh dear. Oh, now I have to reload. Oh, I fumbled. There we are. Go back to the line chart. We see that the next one here is probably, let's try one of these red guys. That's 58B8. There it is. Oh, there's something, case insensitive. That's interesting. That's probably used by our application. So that would be an interesting one to look at, see where the use sites of that are. But maybe we can just look a bit further here. And here we have a B950. And there's another WAI thing. All right, yeah. That was one of them that we saw earlier. And then B910 is another one. Another WAI thing, right? I think these are all the, we just search by slope, or rather sort by slope. Then that is, it'd be really nice if you could actually show the colors associated with the line chart in the detailed view.
Okay, yeah, that sounds possible.
Yeah.
I mean, this is great. I don't even have to do anything in the chat, just everyone's helping each other.
So let's see, what do we have then? CI. Yeah, okay.
Yeah, I mean, don't give too much away, Ben. You maybe perhaps what's nosy.
Well, let's see. So it's an interesting problem. I mean, we have yeah, okay. So I think that we know that there's sort of a few interesting case allocations here. You know, part of it's in case insensitive. That might be used directly by our program, maybe not though. And then there's a bunch of things in WAI. Nothing obviously from our program though, which is interesting. So yeah, what do you want to do next, Matt?
I mean, how people? It seems like people are still
going.
They
okay,
still haven't made quite as much progress as you, Ben. So I think give it a few more minutes.
All right then.
And we'll just take some questions on chat. And I think people, like for the benefit of the stream, people have seen how you have approached the issue and generated the profile.
Yeah.
Right. So Freakenstein, you probably have not linked your application with the event log enabled.
Yeah, that's probably true.
So in the GHD options, when in the cabal file for the real world application, you need to patch -event log so that it links your application with event log support. So I didn't show that when I was doing it because GHD by default is linked with event log support now.
In addition, and with profiling as well. The reason why it complains about profiling is that we also, the profiled way also enables the event log by default now as well, since we have this, the idea eventually is to deprecate the HP mechanism, HP output format, and solely use the event log.
Yeah, which is why I have not mentioned at all the HP format in this presentation.
But it should be, we should mention that eventlog2html also supports HP, at least for the time being, until we sort of finally deprecate it. With the traditional cost center profiling breakdown mechanisms, -hy, -hd, hc, etc. These are all supported by eventlog2html when reading from an HP profile.
Okay, so Evan asks, how much of eventlog2html is dependent on future GHC? The only eventlog2html works with GHC as it is today. It works with 8.10. The new stuff is the stuff you do for table profiling. Everything else works. Detailed modes. Yeah, everything else works.
Yeah. I think it even works with I don't remember when we introduced the event log output. You, Matt? Was that, I think it was 8.8. Yeah, the event log output for profile samples. Was that 8.8? I think it was 8.8.
Yeah, so the support has increased slowly over time. I think in around ZuriHack 2 years ago, I made sure that it worked with the basic modes, and then I added support later for biographical and retainer profiling modes. But HT has always worked, at least since 8.8. and 8.10 or 9, that is rate is pretty solid. Like, I would definitely recommend people use the event log rather than HP at this stage.
That's an interesting point, actually. Yeah. Oh, interesting. Yeah. So.
So Adam raises the point, which is also covered in the README, that he had a non-empty event log file, but eventlog2html produced an empty graph, and this is probably because he didn't quit the server before trying to view the profile. So the event log is written incrementally, but the output is buffered. So if the buffers aren't full and they're not flushed, then you'll get a truncated event log file, which might not contain your samples. So for now, you need to pass the quit the server in order to make sure the buffers are flushed from the event log. There's improvements to this which will happen in 9.2, and I wrote about them in the README, but it turned out the flag was broken. So I fixed that, and it'll get backported and be in the 9.2 release. And this flag will allow you to specify an RTS flag, which will flush the event log at a predetermined period, say 10 seconds, 60 seconds, or so on. So you'll be able to know that your event log file is up to date.
Oh dear. Let's see. What was it? It actually was in the project file, wasn't it?
Okay, so some people are beginning to have found the issue using just eventlog2html, which is good. But and filtering by, like, Andres had a great suggestion of filtering by the by source. That was no, Ben, I think he means dash event log.
Yeah, I just realized that.
Yeah. So filtering by source allows you to look at positions which are from your own program rather than from external libraries. And this allowed some people to quickly identify that one particular source may have caused an issue. And it's right. And I think I suppose what I want to get across with this example is that some people did manage to find where the problem was very precisely using just the detail pane. And that is one way you can use eventlog2html. But there was also quite a lot of noise still present in the profile. And just looking at the area chart or the line chart, there was still a lot of noise with, like, the server doing other random stuff that we particularly didn't care with what it was doing. And that noise did obscure the actual leak. So we did manage to find it this time, but it might not be always so straightforward. And we'll talk about using Ghd Debug to ask more precise questions that will allow us to make sure we find out the answer quite shortly. So we'll give people 2 more minutes until 10 past, and then we'll jump into Ghd Debug.
Yeah, try to identify the problem more concretely in Ghd Debug.
So it's great people have been getting to grips with the tools. My impression is they're not so complicated to use, and what they're trying to show you is quite straightforward. It's interpreting the results which is the hard part. And if it's no longer mystical or difficult to use this kind of stuff, then more people can interpret the results and fix issues. Okay. Right. I'm gonna. So I think we're going to move on now and I'll talk a bit about using Ghd Debug, which probably won't take. Like, maybe we'll talk about that for half an hour or 25 minutes, and then we'll just devote the rest of the session just to if you didn't manage to get this working, then trying to get the eventlog2html working, or trying to use the ghd debug on the application if you didn't manage to get it working, or you can move on to trying it on your own application or something like that. Does that sound good, Ben?
Sounds great.
Great. Right, so let me shimmy back over to my shared screen. 3, 2, 1, and we're back. Okay, so section 3 is going to be all about using ghd debug. And so ghd debug, as we saw before with the ill-fated terminal example, has 2 parts. There's firstly instrumenting the application using ghd debug stub, and this is what we refer to as the debugger. It is the thing we wish to debug. The second part is writing a debugger. The debugger then connects to the debugger and issues requests to the debugger. The debugger understands how to process these requests because we've instrumented it, and then information about the heap or information about those requests is sent back to the debugger. So the debugger can request things like, okay, what are the GC routes for my application? And then once it's got those, it can say, okay, at this address, what is the closure that's there? And so on. And by requesting back and forth with the debugger, you can traverse the whole heap from within a Haskell application without using a very, very large amount of memory. So all ghd debug applications are structured like this. We've already seen how to instrument the program, the debugger, and now we're going to write our own debugging scripts. So we're going to create a simple debugger in order to connect to the server and potentially understand more about this memory leak, if you haven't already understood it. Okay, so let me scroll down past all this.
You need to make it a bit bigger as well, Matt.
Yes, of course.
Yeah.
Okay, so we've already talked about how to instrument an application with ghd debug. You import the ghd debug submodule, and then you just wrap your application with ghd debug. That's it. Then when your program starts, a socket is created, and by default the socket is created depending on what your XDG data directory is set to, but you can also override this by using the ghd debug socket environment variable if you want to create it in a specific place. So when you start your application, the socket is created at that place, and that is where the debugger will connect to and start issuing requests in order to learn information. Simple. Writing a debugger. There is a library which is on Hackage called ghd debug client, and ghd debug client pre-packages a bunch of useful modules in order for you to write your own debugging scripts. Okay, so these are all things that I've implemented when I've been debugging applications, and now they're packaged in a library, so you can use them to write your own debugging scripts. So the first thing we do when we're writing a debugger is we connect to the socket which the debugger is listening on. So the with debugger connect function takes the name of the socket we want to connect on, and then once we've connected on that socket, it will run a debugging script on that connection. Okay, and this is a simple debugging script. So this is a program which takes the debugger, which is the representation of the thing that we are connected to, and then it will perform the series of actions which will issue requests to the debugger and then provide us with useful information. So the first thing you do when you connect is you pause the application. Okay, and you can't do anything else until you pause the application, because if you don't pause the application before you do things, then the garbage collector can move around closures randomly and invalidate the result of your analysis. So the first thing you must do is pause. Once we're paused, we're in a position to query the debugger for information. So the main debugging script is implemented inside the run function. And the first thing you do inside here is we get the GC roots for the session. So what GC roots will do, will issue a request over the socket, and it will say, hey, what are the roots that you care about? And it sends back a list of pointers to me. So ours is a list of pointers, essentially, a list of addresses. And then once we've got a list of addresses, all we're going to do now is call one of these pre-canned library functions that I wrote, which starts from the list of addresses and just traverses the whole heap, summarizing how big the heap is in order to produce some statistics. So all count does is like the most basic script. It takes some roots, starts traversing from these roots and counts how many objects there are, how big they are, and what the biggest object is. And the result of that is something called the census stats, which we return as res. We resume the program, and then we print out the result. That's it. So this is probably the most simplest debugging script there is, and it, of course, heavily relies on the library, which I've implemented. And in this presentation, we're not going to get so much into how count is implemented, as the implementation is not the simplest. But by just using the library functions, you can still get a very, very long way with Ghd Debug. Okay. So right now, I'm going to run this debugger on the real world application, just so we can get a feeling for how that workflow works. So currently the application is not instrumented. So first thing I'm going to do is instrument it, and then I'm going to run the debugger on it, which I've already written. Okay, so we dive into the real world application again. And the first thing we need to do is add the dependency to on Ghd Debug Stub. So I go into the compile file, go to the executable section, and I make sure that there's already a dependency, build depends on ghc-debug Stub. Okay, because that's the package that the instrumentation stuff comes from. So I've done that now, and then I go to app main.hs, import ghc.debug.stub, and I can just say with ghc-debug lib.main. Okay, right, great. Now my application's instrumented. Let's start running the server and see what happens to run the server. Okay. So I'm just building a few things here because I sneakily decided to use my own builder GHC, which has a few more source locations than the ones you have. So we'll just let this run a bit, and then when it starts, it will run an instrumented application. Okay, so now while that's running, let's go over here, and we'll go into the debugger folder, and right here is the program which you saw in the README. So we just connect to the socket and then run the program, which pauses, get a GC's roots count, and then prints out the result. Okay. So I can run the debugger by just typing compile run debugger. And that will run so that builds the debugger. And then it fails right now because the socket does not exist. And this is the sort of error you get if the socket is not yet opened. So it was looking at temp ghd debug for the socket. The socket was not open, so it failed right now. On the other hand, oh dear, we got the old. Well, let me just fix this.
This is strictly because Matt was using his own GHC3 built in GHC.net.
Too right, Bengal, all right, too right.
You shouldn't experience it in principle if you're reproducing at home.
Yeah. If I'm just going to remove the option, I'm just going to exit this. Yeah, so I was trying to use my own tree to build a GHC, which is why I got these errors. Start trying to fancy. and we'll just get the old run server going. It'll probably build some more stuff now. Oh no, it's not. Good. So now it will build the real world application, hopefully. Linking and okay, so now it's good. And now when we start the application, we get this log message which says that ghd debugger started on this socket. Okay, that's good, but it's not the socket we want because we want the debugger to connect on a certain socket which we hard coded. So instead, I'm going to run with ghd debug underscore socket equals temp ghc-debug. Run the application instead of this. So I've now set its environment variable. I've run it, and now it started on the temp ghd-debug socket instead. So now when I run, so now I'm going to start running the what we're going to do. Okay, so I need another terminal. Oh no, dear me. Right. So now I need another terminal to run the requests. And I also need another terminal to. Sorry, I accidentally closed the window. It was very bad. Okay, so in this one, I'm going to run the server. And now in this one, I'm going to start the request loop. Okay, so that's going now. And then in this one, I'm now going to run the debugger again. Okay, so the debugger connected to the process, and it traversed the whole heap and decided there were 9,566 closures. The total size was was this much, and the maximum size of any closure was this much. Okay, so we've written our first debugger there, and it was that simple. And the count is not perhaps the most useful thing on its own to know, but the point, like the count function is provided because if you don't provide something other than GC routes, like say you traverse the heap and find some closures you're interested in, you can also pass them to the count function in order to work out how big a certain closure is. Does that all make sense to you, Ben? You're muted. You have to unmute yourself.
So I do. Yeah. No, so far so good.
Okay. Right. Okay. So that's using count. One of the killer features of Ghd Debug is finding retainer paths, and that's the other example we're going to show today. So what is a retainer path? A retainer path is, say we want to be looking at heap profile and we see all these things to do with responses which are being retained in the profile. We want to know why they're being retained. And the retainer path will give us a path from a GC route to that closure, which tells us why that thing is being retained. So in Ghd Debug, there's this module, ghd-debug.retainers, that provides you a few library functions which allow you to find and visualize a retainer path. Visualize is quite a loose word at the moment, but it will be improved in the future if it's more than just me using the library. So how do we use Ghd Debug retainers? Well, it's very similar to writing the count script. But instead of calling count, we're going to call the find retainers function, which is a pre-built library function for finding the retainer paths. And then once we get back the retainer path, we're going to call this other library function, which adds some more location information to the path. And then finally, display retainer stack will display the paths. Okay, so if we look more closely at the find retainers function, what is the type of that? So the type of find retainers takes a guard to limit the search to a certain number of retainer paths. The heap can get big. If you're trying to find retainer paths to every cons node, your debugger will run out of memory because there will likely be thousands and thousands of different retainer paths. So this limits the search to k distinct objects. It will return the first k paths it finds to k distinct objects. And how does it know which objects it cares about? Well, there is this predicate function which is applied to a pointer and the decoded version of the closure which lives at that pointer and returns a Boolean value depending on whether we care about that closure or not. So in our case, we're going to check to see whether the closure is a constructor and whether it is called response. And if it is, we care about it. And if it isn't, then we don't. So we return false. Then find retainers will start the search from a list of routes, which is given by a list of closure pointers. And the return type is a list of retainer paths. The retainer path is just a list of pointers, where the start is a GC route and the end is one of the pointers that we care about. Okay, so I'll now copy in this this script into my debugger. Where is it gone? Right, so now I'm going to modify my debugger. So copy in this script. So instead of finding type on up, so now I want to find response types. Was that the right type, Ben? What was one of the
yeah, let me check.
Yeah, that's what I said.
Conster. Here, what was your supposition again?
What's that, Ben?
Response.
Yeah, response, or just something that's monotonically increasing in the profile. It doesn't really matter what it was, as long as it's a constructor.
Doesn't seem like it's response. Let me see. Perhaps. No, that's too obvious. One moment. Lenin. No, that's filter by constructors here. And then maybe search.
I think it's request, not response, actually.
I think it might be request, yeah.
Okay, it's request. Okay, so something that's monotonically increasing in the profile, which I don't actually have to hand. Actually, I might have one.
Oh, dear. Oh, I see, because it's in source. That's request or request header.
Okay. Let me try and get that up here. That'll be useful to see anyway. Hopefully this isn't a fixed version. Oh yeah, so this is a fixed version. So yeah, I don't have it locally. But so in the profile, one of the bands that's monotonically increasing that you saw on Ben's screen earlier was this one called request. So we now make this request function, and request is the predicate. Its function is called find retainers, and go is the predicate which we apply to each closure. So which closures do we care about? Well, we care about closures which are constructors which are called request, right? So the first thing we do is like the case expression on the closure sc, and we check if it's a constructor or not. If it's a constructor, then each constructor already helpfully has this constructor description field, which tells you what the name of the constructor actually is. So we dereference that as well, get the name, and we check, is the name equal to request? If it is, return true, otherwise return false. So that's the sort of predicate that you can quite simply write to narrow down the search even further onto specific closures we care about. So that all gets passed into find retainers. We care about the first 100 paths, say, or maybe even 10 will be sufficient. In this case, let's say 10. And then we've got ourselves our second debugging script, just like that. So now, instead of running the program, I'm going to run retainers, and let's see what the output looks like. So I'm going to restart the server because, as noted earlier, you can only connect to a server once when it's instrumented at the moment, because we don't re-listen for more connections. And then I'm going to start in this terminal, I'm going to file new build debugger just to get that going. Oh dear. Right, I just need to import the right module. Right, so I've built the debugger now. So I'll run debugger. Okay. Right. Okay, great. So I start the server, and now I'm going to start the request loop again. If I wait a little while for it to get going, and then I run the debugger, then I get this interesting output. So when I said the output leaves a little bit to be desired, well, it does. Each one of these is a retainer path. So you're starting from the root, which is a TSO, which is a thread state object. And a thread state object references another TSO, which references another TSO, which eventually references a stack. And then that references a function. That function references an stref. And then eventually that references a request. And what's interesting is the difference between the smut var here and this request. So this request is retained because it's retained immediately by a thunk. And this thunk is of type word64. So what's happening is that in theory, what I can deduce from this is that if we were to evaluate this thunk fully, we would discard the request and just be left with a word64 value, which is going to be much smaller than retaining the whole request. Whether I want to force this or not depends on how expensive that computation actually is, but that's a good place to start. And then I look further down the profile and I ask the question, well, why is this thunk being maintained in the first place? Like, if this thunk was never used anywhere, then we wouldn't retain it, would we? So it must be retained by something else. It turns out that that is also retained by another thunk. And that thunk is of type map text word64. And again, we get like quite a nice source location. So let's have a look at what that source location actually is. So I'll stop that. And then this is the best terminal, it's biggest. So now if we look at this, the source location is platform HTTP line 81 3874. So if I open this up here, HTTP, so it was line 78. Okay, right, so we've now zoomed into this request counter thing, and that's got some word64s going on, and it's got some maps going on. And what was that precise source location that we had? Precise source location was 3874. So 3874 is around here. It's here. So that thunk that we're creating arises from this position, and this is kind of like a classic space leak already, because what we're doing is we're inserting this value into a map, but we're not forcing the result of doing the insertion. So we never actually perform the insertion until we look at the value, and that is because atomic modifier oref does not force the result after performing modification. So instead, if we use atomic modifier perform ref prime, then that will ensure that the map gets forced. So Ghd Debug directly led us to this position, despite not, even if we just knew what the thing was being retained, we didn't actually need to look in the profile. We didn't need to like have this clever idea of searching for the source field or looking for all the detailed modes. We could have just looked at the Ghd Debug profile, seen something rising monotonically, looked at retainers, and then immediately been led to the problem. Okay, so if I do that, then let's rerun things and see if that has fixed the issue. Because all space leaks just get fixed by adding a prime, honestly. Surely sufficient.
Bang. That's yeah.
What's that? A prime or a bang?
Yeah.
Good. Right. So the server's running again. We're off and let it run for a little while. Like you notice, I don't need to let it run for very long because Ghd Debug is so precise that even if your space leak is tiny, it will find it. In fact, if it's the bit of space leak, the worse it is, because the output will be thousands of lines long. Like when it's quite small, it's quite nice. So if I run the debugger again, then I get some more going on. And well, why am I still retaining these requests? I think so. There's now different thunks. There's now no map thunks. That's gone. But I still have some thunks going on. I'm still retaining requests. Well, let's look at this position. Here
is type of the thunk of the topmost thunk.
The type of thunk is word 64. So so let's look into that one. So we thought we fixed one leak, but it's actually still leaking requests because it's word 64 thing. So it wasn't quite the right fix. But we can just easily check. We just easily check that again, and now we can look at this one instead. So what is this? 78 to 80. Right. So let's dive in there. So Haskell's got it. It is source platform HT. Oh, where's it gone?
No, CD. Yeah, you're right, but you're not. Platform.
Oh, I'm using CD. Yeah. Okay.
Yeah.
Right. Okay. Right, so now is this what, line 78?
Column 20, okay, so I think it was.
Right, so clearly we're not evaluating len. So len is a type word 64 because that is the thing that gets inserted into the map. But we're not why are we not evaluating that? We're evaluating this map. We're using atomic modifier over, so that should force the value of the map. What type of map are we using? Right. So we're using the lazy version of data.map, which means that the values aren't going to be forced. What if we use data.map.strict? Would that help us? Well, okay. Let's try that. Let's try that. So now data.map.strict is a different version of data.map where the values are forced as they're put into the map. The normal data.map, the values are not forced when they are inserted into the map. So we were still left with this retainer leak. So now I build the application again, and I will run the debugger again, and let's see if we can find anything else wrong. So yeah, let me start the request loop. Chug. And let's see what we've got going on now. Okay. Right, so that looks like it fixed the problem. So now we only have one request returned, which is probably the request which is in flight as we're going. So using data.map.strict was enough to fix this problem. Final thing, we're going to just explore one more thing now. So we use data.map.strict here, but let's say we had not used data.map.strict. Let's say we hadn't thought about it very closely what the actual fix should be. The problem was we were certain things in the map but they weren't being forced. Is that the same thing as adding a bang pattern to the len before we insert it into the map? Well, let's try. A legal bang pattern. Oh dear. So I'm going to add the bang pattern to len. And this example just highlights how you must carefully think about things, because I'm expecting there still to be some kind of small space leak, but perhaps it's not to do with requests anymore. Because if you add the bang pattern here, then you will force len, so you no longer retain the request. But you're not going to force the result of applying plus to all the word 64s. So you will end up with a thunk, which is an unevaluated addition chain in the program. So I'm now going to switch back to using eventlog2html and run a quick profile of this, and you'll still see there's a thunk leak. And this will round things off quite nicely. So I'm now going to start the server. Plus RTS -hi. Well, let's just -ht-l. Library So I'm just going to add the right options here. GHD options, eventlog. Okay. And I just run the server now. So I'm now going, oh dear, what's going on here? What can you see what the problem is, Ben? Oh, I'm passing it to you. I'm sure everyone in the chat is saying the issue is that I'm not doing this.
Yeah.
Okay, so now I've started the server again. I start running, and now I'm going to just let this go for a little while, and then I'm going to generate the eventlog2html output. And if fingers crossed, if I've been correct, then we'll still have a thunk leak. And yeah, it was something we could investigate further with Ghd Debug, but it's a sort of very subtle thing that could easily, like inserting bang patterns where Ghd Debug says you should, is again not how to proceed. We have to think about, Ghd Debug tells us where the problem might be, but is that the correct way to fix the problem just by forcing that thing? Probably not. Like, we have to think carefully about the structure of our programs. We are at the end of the day, the architects of our programs, we understand the domain, the tool does not. So think about it before acting. Right, so I'll stop this now, and we'll have a look at the profile. Eventlog2html, and we will ghc-debug. And if we go into the browser, and we look at this, then there's likely going to be quite a lot of noise from all the extra stuff that's going on. Well, the profile looks pretty flat here. Like, what am I complaining about? Oh, is this the right one? No, this is the wrong profile. What happened there, Ben? Did I generate the...
That's a good question. You done messed up.
I messed up here.
Yeah.
15. Oh, no, that's right. I think I see to refresh. No. Profiling 0.
Maybe just delete it and we
should
remove
be
any
right.
question.
I think I'm in the wrong. Oh yeah, I'm in the wrong directory. That's why. Yeah. I'm in the wrong directory. Here we go. Right. So now if I look at the profile, we get this very spiky profile. So it's not obvious anything is actually wrong. It looks a lot better than before. But now I'm going to look here, and actually, you see this. What do we see here? We see a monotonically increasing band. So after like 100 requests, it's not a problem. After 1,000 requests, it's not a problem. But what about 10 million, 100 million? There's still an issue. So this is the sort of thing we could look into more with Ghd Debug. And we can see here the problem, like the word 64 band is also monotonically increasing. So the problem is something to do with thunks retaining word 64s, which is something that I'll just quickly modify Ghd Debug, and we'll be able to see that issue manifest as well. So how do I modify Ghd Debug? Well, we go to the Debugger script. And instead of looking for requests, we're going to look for word 64 hash constructors, because that is what this constructor is called. Okay, so I'll just look for 10 of those. Don't need to modify anything else. And now I'm going to type devel run debugger. I'm going to start the server again. Where are we? So run the server again. Now run this for a little while. In fact, I don't really need to run it for that long. If I just run the debugger now, I need to just run it with the socket. So I say run for a little while. Then this leak is tiny, really small. But if I run the debugger, then I get told, like, okay, this word 64, which is allocated at this point, is retained by this stunk. And this stunk is retained by this stunk, and this stunk is retained by the bin constructor in data.map. And I don't get any precise information about this stunk because it's actually a generic, the generic application thunks, which is built into the RTS because it arises from inside data.map, and data.map does not know which function it will apply to create the thunk. So there's no location information, but by looking at the retainer path, I can see, oh, there's a thunk in bin here. Perhaps the fix is to use a strict map rather than inserting that blank pattern. And you can see that, okay, there's various sizes of thunks here, and this is just going to increase more and more over time. So I think that's a good place to end things. We've seen how Ghd Debug can allow you to really get to grips with the small details, and I think now it's like it'd be good if people wanted to try and replicate the examples I've shown in this section, and ask any questions they've got. And while we're here for the last 15 minutes to help out with anything like that.
Yes, excellent. Yeah.
So I don't know if you want to share your screen, Ben, again, and just try and reproduce what I did. I suppose I've already done that, but
no, it doesn't.
I make it look easy because I've written the library.
No, that's right. You get to, it's much more fun to watch me stumble about blindly.
This time, luckily, you've already installed Docker and already restarted all your NixOS systems, so it'll be an absolute breeze. So yeah, I'll stumble into chat and stop sharing my screen, and Ben will share his screen for the last 15 minutes, and then we'll take it from there.
Yes. Yeah, I do hope we can get a sort out with Apple, and this will all be much easier once this is all released. Once GHC 9.2 is out, and the Cabal patch. This is all a bit hairy because of how much pre-release code you need to reproduce all of these things. But yeah, it's going to be, the future looks very bright.
Can you increase your font size then, perhaps?
Of course, yeah. There we go. That's no, probably not. There we go. Oh, yeah. All right, so let's see here. Right, okay, so let's see, where were we here? All right, let's start by taking and... All right, so I believe actually I already applied I've added with the ghc debug to the application main entry point. So this is, in principle, this should work. I believe if I say, what was the name of this? Nope, that was the wrong. All right. Yeah, fine. This is a bit too big, perhaps. Let me see, library, and here's the executable. Yes, right there, and ghc debug stub. All right, so in principle that should, what was the name of the executable? Real world exe, I think it was. Real world exe. Great. Let's see. What are your thoughts on the relation of memory profiling and performance profiling? Yeah. So I suppose that would be like the latter, you mean runtime profiling, like the actual time profiling as opposed to space profiling. And that's a good question. This is actually the work, the company rather, that had sponsored, that sort of enabled the ghc debug work is actually also, we're still working with them. There's now funding work on that may potentially enable use of perf, the Linux time profiler, and general PMU profiler on Haskell programs. So in particular, Andreas Klebinger is currently working on reworking the Haskell execution model, ghc Haskell execution model, to, oh really? Oh, brilliant. To use the system stack pointer, which should allow perf to be able to unwind the Haskell stack more readily, and I'll enable call graph profiling with perf. So this is something, if you look at the blog post I published probably, I don't know, 4 months ago, perhaps now, on the GHC blog. It's also cross-posted on the well-typed blog. There's a series of 5 posts about dwarf debugging, dwarf support. The last post, I think it was, or maybe the post 4, I think that was probably the one, describes how this might work to enable real, like, cross-language call graph profiling, which is very useful if you have like a larger system in a polyglot setting. Enables really holistic profiling, a good holistic picture of what the system as a whole is doing. So that's a possibility. And we still have yet to know whether that's actually going to work out performance-wise. It looks, GHC's existing register assignments are chosen the way that they are for a reason. It's very likely that code size will increase by 1% or 2 in changing the stack pointer as we're planning to do. Whether that affects actual runtime it remains to be seen. It's kind of a question of how the microarchitecture optimizes, is able to how much this affects instruction level parallelism and such. So we have yet to know. But regardless, it's that will happen hopefully in 9.4 if it happens. Otherwise, we'll be looking at other options for enabling perf. Evan, technically you can use perf today on a suitably compiled program, but you cannot get a call graph from it. So you get a sort of a flat time profile. You know how much each function, how much CPU time each function uses, but you don't know that it was, a f called by g called by h, etc. It's often very useful to have a call graph. Flat profiles are rather hard to interpret, especially in a larger system. Anyways, I'm going to try to focus here on reproducing Matt's thing here. Now, what is going on here? This is very interesting. Somehow, I managed to break Postgres. That's fascinating. You have any idea what's going on there, Matt? Oh, Matt left. Oh, okay. Fair enough.
So I was just having a bit of a lie down, Ben.
Oh, I see. Okay.
After
yeah.
After going at it for a bit.
Yeah. No,
Postgres.
quite all right. Yeah, my password seems.
Wait, it seems to be retrieving the have you modified the?
Strangely, I haven't. This is new.
Okay. No. Ben, you're not passing the post. You need to use the run server script because you're not passing the.
Oh, quite right. Yeah, that's right. We need to go to the yes. Right, of course. Yeah. Thank you.
Hopefully, set up all these environment variables for you, so it will work.
Yeah. There we go. All right, brilliant. And now, if we do we run the workload. Run. All right, so the workload is now running, and in principle now we can say, let's see, the the test, how was it here? Right. Right. All right, we're off to a good start. Okay, we'll just take this then. That's fine. Yeah. Actually, no, you know what? Let's just do this. All right, so we're going to override the socket. There we go. All right, now the workload is running and we can connect. Brilliant. All right, and there we go. Now we have our, there we have our retainer path. And we see indeed that we have, there's the thunk that was, indeed, you can see, in fact, even more than the fact that, so we have the request that is retained, we have the thunk that retains it, which is this word 8, and we have a few maps, and there's only a couple here because we haven't done many insertions yet. But then we see that this is reachable from this mute var, this stref, which is an IO-ref. They're the same in GHC internally. And if we look at that, we see indeed that, yeah, that's size ref that is retaining it. At this function, which I suppose is probably.
I mean, Ben, the line was like line 33, right? Which probably.
Oh no, right. So there, we've already found this though, so there's no real reason to, I think we.
Right, no, but the stref also says a location.
That's right. Oh, right. Yeah, 33.
Line 33.
Yeah, we can look at that. Although that is not actually the most. Yeah, well, okay. So that didn't quite work out as well as one would hope.
Well, it's just, I mean,
it was allocated here. Yeah. But yeah, that's the.
For some reason, it's, I don't know why that. Yeah, like the positions aren't but it's quite close. It's quite close to where it actually was created.
3 lines is not bad. It's within spitting distance, and yeah, and then in addition, we see this function here, and if we look here, that's let's see, line 55. That is indeed this middleware. That we've added. So it's this closure here that captures presumably the no, okay. Oh yes, the IO-ref. There it is. Yeah, that's the IO-ref resp. And so that is the closure that is capturing it. So we have the whole path. The reason there are multiple TSOs here is that there's actually a sort of the scheduler has a linked list of threads in the run queue. So this is actually the starting from the head of the list, and this is like the 5th thread in that list, and it's stack, and then something else. I don't actually know what this is. That's an interesting. But then we have the IO-ref and etc. So there we have it. So all in a matter of 5 minutes, managed to pin down the culprit. Pretty good. And the nice thing about this is that time is not, unlike sort of cost center profiling, the time doesn't scale strongly with the size of the program. So you can, regardless of sort of the size of the code base, the profile is going to give you a very precise answer, very precise pointer to where the retainer is being allocated.
Yeah, okay, that's great stuff, Ben.
Yeah.
We've got a question from the chat from Evan and Li Yang about pause behavior. And they have observed that the current way things work is you have to pause the debugger from the debugger, which it's not always what you want, because sometimes you want the debugger to pause itself once a certain event happens, then pass control off to the debugger in some manner. And that is a good point. And the reason why it doesn't currently work at the moment to pause the debugger and then pass control off to the debugger, or what I should say is that you can pause the debugger and pass control off to the debugger. There is support for that using a polling mechanism, but then you can't unpause the debugger again due to some complications to do with. Do you remember why you can't do it, Ben? There were some complications to do with.
It was something, yeah, capability ownership or something like this.
Yeah.
I don't recall. It's something that can be fixed, but yeah.
Yeah, it's not been a priority to fix yet because we haven't needed it. We find that you can engineer your program to stop at a certain point by inserting like get line or something like that, which is sufficient. But if we're perhaps in future we can fix this bug, because the essential issue is that the debugger calls pause itself, which suspends the execution, but then the call to unpause comes from a different thread because that is triggered by the debugger, and for some reason the RTS doesn't like this, and it's not been a high priority yet to look into why that is the case. We've also thought about triggering pauses based on RTS events, such as, okay, my application is now going to quit because of a heap overflow. Perhaps now is the time that we want to create a dump of the heap, and then look into that later. There's support for that. There's not support for the pausing part, but you can currently create heap dumps, which you can then analyze offline as well, which is a nice mode of usage. And there's also experimental support for forking, which would mean that instead of pausing the application, you fork it. And then you can interact with the forked application whilst the other application continues to run. And this potentially has quite high memory overhead, but it means that you can quickly take a snapshot of the program without having to completely stop execution for a period of time. And again, this is not well tested and has resulted in seg faults before, but it has not been a high priority to fix because I haven't needed to do it myself. But these are all things we can look into in the future if users need them.
Yeah, you say that it incurs high memory overhead, and indeed it's high in the sense that it doubles memory consumption. You have to have 2 copies of the program in memory after you've forked, at least after you've started to mutate a bit further. So, yeah, it's high in that sense. Yeah, MMH. I'm not sure which. What are those? What is the? I think I missed the context here. But yeah, so we also it is 11 o'clock now, so we're pretty much done. That is kind of the end of the road for us. If anyone has sort of be happy to stick around for a bit longer. If somebody has like a problem that they want to try to throw these tools at, and they think it's small enough that we could compile and potentially have a look at it in the next half hour or so. But otherwise, it's just happy to discuss. Yeah, these compact region questions. I see. Yeah.
Yeah, Ben, let's perhaps call it a day there on the stream, and we can take the questions on chat, and I believe Discord has a voice chat facility still.
Maybe we could all just if you're interested, drop into a voice channel and can.
Yeah, but I believe it's a nice place. Let's round it off here.
Yeah, so I think that's right. Okay.
So yeah.
All right.
Awesome. Well, thanks everyone for tuning in, and see you next time.
Indeed. See you in a moment.
Right, how do we quit this thing, Ben?
I don't know.
How do we get out of here?
Get me out.
Okay,
here it goes.